Conditional probability and expectation, an introduction. Our objectives for this demonstration are as follows: to introduce the conditional probability, to introduce the mathematical expectation, to compare conditional probability with traditional probability, and to interpret the results of conditional probability and expectations. Some materials to review. We're going to need to review some probability, some arithmetic processes, and independent and dependent events. Let's begin with some terminology. Let A and B be two sets in a sample space S. Then the probability of event B occurring, given that event A has already occurred, is called a conditional probability. Conditional probabilities are denoted as P of parentheses B pipe A, and is read the probability that event B occurs given that event A already occurred. Here's another definition. Let S1, S2, all the way up to Sn be the possible numerical outcomes of an experiment, and let the probability of S1, the probability of S2, all the way to the probability of Sn be the probabilities of those events. Then the mathematical expectation, or just expectation, of the experiment is this formula below, which merely says that we sum up the products of the numerical outcomes times the probability of receiving such an outcome from this experiment. And we'll see a lot of examples of this in this demonstration. So in order to compute expectation, we do the following steps. 1. Determine the numerical value of the outcome of each experiment conducted. Step 2 is to determine the probability of each outcome from the experiment. Step 3 is to multiply each outcome with the probability of that outcome. And the last step is to sum the results of step 3. The formula for the conditional probability, the probability of B occurring given that A has already occurred, is shown here. And this basically says that the probability of B occurring given that A has occurred is equal to the probability of A and B both occurring simultaneously divided by the probability of A occurring. Here are some rules for conditional probability. And the first one listed here simply says that the probability of the event A occurring, given that the event A has occurred, is simply equal to the probability that A occurs. The probability of event A occurring, given that B has already occurred, is not the same, or is not equal to, the probability of event B occurring, given that A has already occurred. So you cannot interchange the order of the sets when it comes to whether one occurs first or second. These are not commutative, in other words. The probability of A occurring, given that B has occurred, will be equal to the probability of A if and only if event A and event B are independent events. Now here's a Venn diagram for the conditional probability. First, we're going to zoom in on the set where the event has already occurred. So we're going to zoom in, and zooming in essentially sets up set A as the new universal set. Remember, the conditional probability is used when an event has already occurred. So the Venn diagram for the conditional probability for the probability of B occurring, given that A has occurred, can be drawn in this fashion. And what this basically suggests is that the probability of B given A, or the probability of event B occurring, given that A has already occurred, can be measured by how much area event B has inside the set A when it comes to Venn diagrams. Now, Venn diagrams are usually not used for their area computations, but graphically speaking, using Venn diagrams, this is one way to interpret that information. So how much of B actually carries over into A is one way to think about a diagram for the conditional probability. And as it says down in the corner, the amount of shading in set A that comes from set B is equivalent to this conditional probability. In this section, we focus our attention on conditional probabilities and comparing this new probability with the traditional probability calculations. So let's recap some probability. Determine the probability of obtaining a face card with a standard 52 card deck. Since there are 3 face cards per suit, and for suits, there are 12 face cards total that fall under the event. There are 52 cards total to choose from, so the probability can be computed as 12 divided by 52, or 3 divided by 13. Now for conditional probability, we're going to add in some information. Let's say we know the card is a heart. Now what is the probability of it being a face card? There are now only 13 cards to choose from, since there are only 13 cards that are hearts in the deck, that belong to the suit of hearts. The number of face cards that are hearts is now only 3. You have a king, a queen, and a jack. So the probability of having a face card, if we already know that it's a heart, is 3 out of 13. While the probability is the same for this example, the sample space, and thus the total number to choose from, changes. The probabilities will not always be the same when the sample space changes. So let's look at another example, and let's change the information again. Let's say we know the card is a face card. Now, what is the probability of it being a heart? The number of face cards in a standard deck is 12, and the number of hearts in a standard deck is 13. But we know it's a face card, so there are only 3 face cards that are hearts out of the 12 total face cards in the deck. Therefore, the probability is 3 over 12, or 1/4, and not 3 over 13 as before. So the kind of information that's given to you can dictate how the probabilities will be calculated. So using a formula for conditional probability, suppose the table below demonstrates the effectiveness of a flu vaccine in preventing the onset of the flu. And here you can see the information. Determine the probability that one person selected from this population contracted the flu, given that the person received the vaccine. So now we have an additional piece of information. First, we translate the question into a probability statement to help us organize the process. Since we are looking for the probability that a person contracted the flu, given that they received a vaccine, we have the probability of event F given event V. And we're going to define F to be the set of individuals who contracted the flu, and we'll define event V as the set of individuals who received a vaccine. So now we have some notation out of the way, we have some organization to help us with the problem, so let's go ahead and proceed. The formula is the probability of contracting the flu given that you received the vaccine can be computed as the probability of the event contracting the flu and receiving the vaccine occurring divided by the probability of getting a vaccine. So we need to determine the probability of F and V together and the probability of V. Now remember, F is contracting the flu, V is receiving a vaccine. Below we have the table reproduced to see what events are of interest in this example. The number 21 is circled here because this is the number of successes for those who contracted the flu and have the vaccine. So this number is the number of F and V. So this is the number of individuals who contracted the flu and had the vaccine. The number 490, this is the total number possible. This is the total number of people in our group of interest. So this is the number in the entire sample space. The ratio of these two numbers will form the probability of getting the flu and having the vaccine as compared to the entire population. So 21 divided by 490 will be that probability. The number 219 is the number of successes for those who have taken the vaccine. So this is simply the number of individuals in the set V, or the number who have the vaccine. And this is again is the total number possible. So the ratio of these two numbers, 219 to 490, forms the probability of getting a vaccine. So the probability of getting a vaccine is 219 over 490. Again, the probability of getting the flu and having the vaccine is 21 over 490. And substituting these into the formula, we have 21 over 490 divided by 219 over 490, and that gives an answer of approximately 0.096. So there is approximately a 0.096 probability of someone contracting the flu given they have the vaccine. Or, if you like, you may say about 9.6%. Using the information from the previous example, determine and interpret the probability of getting a vaccine given that you have contracted the flu. The question is asking for the probability that one person selected from the population received the vaccine, given that the person contracted the flu. This is not the same question as the previous example, since the given events are different. Below we have the table reproduced to see what events are of interest in this example. Again, 21 is the number of successes for those who contracted the flu and have the vaccine. So this is the number of flu and vaccine recipients. Again, 490 is the total number possible out of this group. The ratio of these two numbers will form the probability of getting the vaccine and the flu. But now we have 97 circled, and this is the number of successes for those who have contracted the flu. Whether they have the vaccine or not, doesn't matter. These are the number of individuals who contracted the flu. So this is the number of people who contracted the flu. And again, this is the total number possible in our sample. And the ratio of these two numbers will form the probability of getting the flu. Now we have PF from the table, and PF is 97 over 490. The probability of F and V, again, is 21 over 490. Using this formula, because this is the formula that we're going to use to compute the conditional probability, we go ahead and plug in our ratios, 21 over 490 divided by the ratio 97 over 490, and that comes out to be 0.216. So the probability of someone being vaccinated, given they have the flu, is approximately 0.216 or 21.6%. This next example demonstrates how conditional probabilities may be computed if you play blackjack, knowing what the dealer has. This aids in your decision to accept another card, being hit, so to speak. If the probability is high, the next card keeps your total at most 21, it is likely you will accept a hit, so you will take another card. If not, then you would stay. And there are several examples demonstrating this situation. The rules for blackjack are actually pretty simple. Numerical cards are worth their stated value. Face cards are worth 10. Aces are worth 1 or 11. And the goal is to try to have a total of 21 without going over, and also to have more than the dealer. So let's suppose the dealer has a 5 and a king. Then the dealer's total is 15. Let's also suppose that the player has an ace and a 3. The player's total is 14. Determine the probability of the player drawing the next card that puts his hand closer to 21 than the dealer's. To determine this, we'll do the following. We determine what cards are available for the player to have more than the dealer, but not over 21. And these cards are as follows: 2, 3, 4, 5, 6, and 7. There are 4 2s available. There are 3 3s available. Remember, 1 was already in play. There are 4 4s available, 3 5s, 1 again is already in play, 4 6s, and 4 7s. These are the cards that are available for the player to receive, to be over the dealer's hand. Add up the total number of cards available to the player to have a better hand. And when you add up the total number of these cards, you get 18. There are 18 cards total available to the player, so that the player will have a better hand than the dealer. To determine the probability, we divide this number by the total number of cards available. In this case, 48 cards are available. So we have 18 divided by 48, or 3/8, or 0.375 as the probability of the player obtaining a better hand on the next draw of a card. Here's another example. So here the player has an 8 of hearts, so right now he has a stated value of 8. The dealer draws a 9 of spades, so the dealer has a stated value of 9. The player draws the 6 of clubs, so now the player has 14 showing, 8 plus 6. And the dealer draws the 10 of hearts, giving him a total of 19. So the player has 14 and the dealer has 19. Determine the probability of the player obtaining a higher hand than 19 but no more than 21. So the player has to draw specific cards on the next hit in order to have a higher hand than the dealer. The player must draw a 6 or 7 on the next card in order to have a higher hand than the dealer. A 6 is already in play. Remember, the player has a 6. There are 48 cards left. 3 of them are 6s and 4 of them are 7s that are still available for the player. So the player has a probability of 7 out of 48 to get a higher hand than the dealer on the next draw. A third example. Right now the player has 3. The dealer has a king, which counts as 10. The player draws a queen, which also counts as 10, so now the player has 13. The dealer drew a 7, so the dealer has 17. The dealer has 17 and the player has 13. The player must draw a 5, 6, 7, or 8 in order to beat the dealer. There are 4 5s, 4 6s, 4 7s, and 4 8s available in the deck. And there are 48 cards left to choose from. The probability of the player having a higher hand on the next draw, but having no more than 21, is 1/3. Our next example deals with dice. Given two dice, one with 6 sides, a standard die, and one with only 4 sides, called a tetrahedron, let's determine the probability of getting a sum of 6 when we roll these dice. First, we generate a sample space for all possible outcomes of a roll with these two dice. A table is best suited for displaying the results, and the next slide shows the sample space for rolling these two dice. So here is our sample space. We have the 4 possible outcomes on the first row, the 6 possible outcomes on the first column, and then we have all the pairs of outcomes that come up in between, all 24 of them. And our job is to determine which one has the correct sum, the one that we're looking for. So to determine the probability, we have to determine the number of ways to get a sum of 6 with the rolls. In the next slide, these options are circled. So here we have 5 and 1, 4 and 2, 3 and 3, and 2 and 4. These are all the possible rolls that will sum up to 6. Now some of you may be wondering, is 4 and 2 and 4 the same? And the answer to that is no, not in this case, because the 4-2 combination is a 4 on the 6-sided die and a 2 on the 4-sided die. Whereas the 2-4 combination is getting a 2 on the 6-sided die and a 4 on the 4-sided die. So they are not the same outcome. Note that we have identified the pairs whose sum is 6. We have 4 of these pairs. The total number of possible outcomes is 4 times 6, which is 24, the number of entries in the table. So the probability of getting a roll whose sum is 6 from these two dice is 4 out of 24, 1/6, or 0.1 with the 6 repeating, or approximately 16.7%. In this section, we address the notion of independent events and the multiplication rule for probability, since the conditional probability involves both of these concepts. If the events are independent, meaning that the occurrence of one event has no bearing on whether the other event occurs, then the product rule for the probability is as follows. The probability of event A and event B occurring at the same time is equal to the probability of event A times the probability of event B. And this is what it means to be independent. So if events are dependent in some way, though, then the product rule for probability becomes as follows. The probability of A and B occurring is equal to the probability of A occurring times the conditional probability of B occurring given that A has already occurred. Notice that if events A and B are independent, then the probability of B given A is simply equal to the probability of B, since the occurrence of event B does not depend on whether A occurs or not. The probability of 2 or more events occurring in succession is the product of the conditional probabilities of each of these events. Here's an example demonstrating the product rule for independent events. A pair of dice are tossed twice. What is the probability that the first roll is a sum of 7 and the second roll is a sum of 11? The rolls of a pair of dice are independent. The probability of a sum of 11 on the second roll does not depend on the outcome of the first roll. So let's let A equal the sum of 7 on the first roll, and let's let B equal to the sum of 11 on the second roll. The probability of A and B both occurring is simply equal to the probability of A occurring times the probability of B occurring. Now there are 6 ways to get a sum of 7 out of 2 standard dice, and there are 2 ways to get a sum of 11 from 2 standard dice. Multiplying these two fractions together that you see here, 6 divided by 36 times 2 divided by 36, and reducing simply gives us 1 over 108. So the probability is 1 divided by 108, or approximately 0.00926. This is 0.9%. This is less than 1% chance of seeing such an event. Suppose a standard deck of cards is shuffled and 3 cards are dealt. Find the probability that the cards dealt are a spade, followed by a heart, followed by another spade. Let's let A be the event that a spade is dealt first, and let B be the event that a heart is dealt second, and let C be the event that a spade is dealt third. Again, this helps with organizing the problem, getting it ready to perform calculations. So now we have the following to compute. The probability of A, probability of getting a spade on the first card being dealt, is 13 out of 52, or 1 out of 4. And that makes sense because there's only 4 suits in a standard card deck. But the probability of B given A is equal to 13 out of 51. There are 13 hearts to deal from, but now there are only 51 cards left, since the spade was not replaced. The probability of C, given both A and B have occurred, becomes 12 out of 50. There are 12 spades left to deal, and there have already been 2 cards dealt. So we had 1 spade being dealt already in the first card being dealt, and we already dealt out 2 cards to get to this third card being dealt, so that leaves 12 out of 50. Now multiply each of these results together, and you get this 0.01, 529, etc. So the probability is approximately 0.015, or approximately 1.5%. In this section, we focus our attention on mathematical expectation. We demonstrate how to compute and interpret the results for such a concept. Suppose you wish to participate in a raffle. It costs $1 to buy a raffle ticket, and if you win the raffle, you receive $1,000. But you also discover there are 9,999 other players in the raffle other than yourself. What is the expectation that you win? We use the formula. We take the reward or loss for the particular result of the experiment and multiply it by the probability of getting that event. In this case, we only have 2 possibilities. Either we win or we lose. So for our example, we have -1 times 9999 divided by 10,000. Now the -1 is the dollar you spent to play the raffle. The 9,999 represent the other individuals who will also play out of the 10,000 total individuals playing. So that first event, that first calculation I should say, is simply the probability that you do not win. You will lose $1, that's the loss that you experience, and the probability of that occurring is 9,999 over 10,000. But the reward that you get is $1,000, but there's only 1 chance out of 10,000 of getting that $1,000 reward. So the second calculation, the 1,000 times 1 over 10,000, represents the part of the experiment where you actually win. And you add these up together and you get a negative 0.8999. The interpretation of expectation is definitely something that needs to be explained. What the results of this example do not mean are as follows. Whenever an expectation in a game is negative, it does not mean this is what you lose after 1 play. That is not what it means at all. It also does not mean that the chance of you losing is high. Expectation is not the same as probability. Probability measures the chances of success or failure based on the number of favorable outcomes with respect to the total number of possible outcomes. Okay? Expectation is not that calculation. Expectation is the reward or loss associated with the result of an experiment. And then you add all of those up. So what does this mean for this example? It does mean that in the long run, if you were playing many times, this is the amount that you would be expected to lose. In other words, you would be expected to lose after many, many times of playing about $0.89 or about 90 cents. When a game has a negative expectation, it is advisable not to play, as playing in the long run would result in a net loss. It does not mean, okay, let me remind you, it does not mean that you are going to lose every single time. That's not what it means at all. Expectation deals with long runs, many plays. And the reason why this is associated with it is because we are using the theoretical probability. What is the chance of something occurring after many experiments have been conducted? So expectation and probability are linked by considering many experiments being run, many experiments being run. Okay, the probability is then the chance of seeing such results after many experiments are run, and the expectation merely associates with those probabilities a reward or loss and adds up all of those possibilities, and then you have an expectation, what you are expected to see or experience after many runs of an experiment. Here's another example. According to mortality tables published in the National Vital Statistics Report, the probability that a 21-year-old will die within 1 year is approximately 0.000948. Suppose that the premium for a 1-year $25,000 life insurance policy for a 21-year-old is $32. What is the insurance company's expectation for this policy? Let's let D represent the event that a 21-year-old person dies during the year. Then the probability of this person dying would be 0.000948, and the company must pay out $25,000. Because the company charged $32 for this policy, the company's actual loss is merely $24,968. They keep the $32, in other words. Let's let L represent the event that a 21-year-old person does not die during the year. Then the probability of them living would be 1 minus this 0.000948, which is about 0.999152. The company also keeps the premium. The expectation would be computed as follows. Expectation is the probability of a person dying times the amount that they would lose because the person died. And then we would add on the probability that the person lives times the reward of that person living. And when you plug all of these numbers in to the calculation, you get about 8.3. The company's expectation is $8.30. So the company will earn, on average, $8.30 for each policy sold. So again, this is talking about many 21-year-olds accepting this policy from this company. Many 21-year-olds. So this is kind of like an average, or what they would expect to receive after all of this. Okay, 21-year-olds can die during the year. The probability of that is very low. And because the company keeps the premium regardless, the rewards and losses to the company are given as 32 and negative 24,968 respectively. That's where those numbers come from. So on average, or in the long run, an insurance company will have a positive amount from the policies. Thank you for your time and attention.